21.
Hello. How are you guys today? Stressed? Did she finish lecture material yet today, or is she still teaching new material for tomorrow? Oh, she did? Okay, that's good. Did she end up like with the helper reactions for electrophilic aromatic substitution, like desulfonation, oxidation with peroxy acid, oxidation with drones, reduction with clemency reduction, hydrogenation, iron HCl, and what was the other one? Protecting NH2 and H groups. I think that was the activators controlling positions, right? I see. Okay, like determining what groups will take priority over the others. Okay, so what I plan to do for today is, do you guys want to go over the practice midterm from beginning to end, or is there any problem that you guys want to start off with first, or any topic that you guys want to start with first? Okay, yeah, let's do it from beginning to end, right? So let's do the reactions right here, where we have this benzene with this alkyl halide or haloalkane attached to it with AlCO3 catalyst, right? And let's also practice the mechanism as well, because that could show up on the mechanism problem on the midterm, right? So what reaction do you guys think is going to happen when you have this benzene with a haloalkane attached to it and AlCO3 catalyst? I'll give you a hint. It's one of the EAS reactions. It's one of the electrophilic aromatic substitution reactions. Okay. Friedel-Crafts, right. And there's two types of Friedel-Crafts. Would it be a Friedel-Crafts alkylation reaction or Friedel-Crafts acylation reaction?
Where is it?
Right. So Friedel-Crafts, the difference between Friedel-Crafts alkylation and acylation is that alkylation does not have a carbonyl. Right. Friedel-Crafts acylation will have an acyl group or a carbonyl. So the reagents you see for that is something like this, with a acyl group or carbonyl group. And second step, acid workup, right? Or instead of an acyl halide, you could also see an anhydride like this, right? Where the thing that you're attaching to the benzene is going to be this highlighted portion right here. That R group with the carbonyl, the R group with the acyl group, right? That's the thing that's being attached to the benzene ring. Where the halogen here, chlorine, or this acetate there, are going to be the good leaving groups, right? So when you see an acyl group or carbonyl, then that's Friedel-Crafts acylation. But because we don't see any carbonyl here or acyl group, then this is going to be Friedel-Crafts alkylation, right? And in EAS reactions, they're going to be condensed down into these three general steps in the mechanism. The very first step is to form the electrophile. The second step is to add the electrophile onto the benzene ring, which is the addition step, which would break the aromatic benzene ring. Like, I'll show you that more clearly as we go through this mechanism. And to restore that aromaticity, we're going to do an elimination reaction to reform that double bond, but more specifically an E1 reaction, right? So now, when you see this halogen here with the metal catalyst AlCO3, this aluminum has an empty p orbital because it has 3 bonds to chlorine already, so it has 6 electrons. But think of it like boron. It's one of those weird atoms that is neutral with 3 bonds with 6 electrons, right? But it is still an empty p orbital, making that a Lewis acid. And we could also refer to that as a metal catalyst in this reaction, because that will get reformed in the mechanism. This AlCO3 here is a metal catalyst because this will get reformed in the mechanism. Right, so let's get started with the mechanism. Let's do the first step. Form the electrophile.
Good.
Right. So let's say we have that benzene ring right here.
Oops.
Right. The halogen here with pairs of electrons will
For me to learn how.
attack the metal catalyst here, where this aluminum has an empty p orbital, right? And that's going to give us this intermediate right here. Where that halogen that attacked that aluminum is going to have 2 bonds, making that positively charged, right? And this aluminum has 4 bonds, making that negatively charged, right? Now, think of this as an SN1 like mechanism now. It's not always going to be SN1. It could be SN2 depending on what intermolecular reaction you have, like what kind of ring you're forming. But let's say that this right here is our very good leaving group, right? Think of it like chlorine or bromine, any good leaving group, right? And if it's SN1 like mechanism, can we kick off this good leaving group off to form this primary carbocation right away first? Is that going to form a stable carbocation? Or do we have to do a concerted shift first? Right, so yep, we have to do a concerted shift because when we kick off this good leaving group right here, like that whole group right there, it's going to form a primary carbocation, right? So that's too unstable to exist. It's not going to leave by itself first. But we can do a concerted shift here where I'm going to explicitly draw out this hydrogen and shift that whole hydrogen onto that carbon and kick out the leaving group at the same time, right? So now that's going to give us this carbocation intermediate here, right? And then the leaving group that left is going to be this right here. And if this was a mechanism problem, make sure to draw this out as well, right? Because this will count as points. Now, this is the end of the first step. We have our electrophile now, which is this carbocation. Now, let's move on to the second step, which is the addition step, right? Where, let's say, one of these carbon atoms here is the nucleophile. That's going to attack that carbon right there because that's going to form a 1, 2, 3, 4, 5, 6-membered ring, which is a very stable ring, right? We don't want to use this carbon to attack because that's going to make a 1, 2, 3, 4, 5, 6, 7-membered ring. That's less stable, but that's too far away. So I'm going to use the bottom carbon here to attack this electrophile right there, right? And this is an intramolecular reaction. So I like numbering my atoms from the nucleophile and end my numbering system to the electrophile. So that's my 1, 2, 3, 4, 5, 6 chain right there, right? Where I'm going to draw out that template right here, where this is my 1, 2, 3, 4, 5, 6 carbon chain that I numbered right there. This is the star, this is the dot, right? The star attacked the dot. That's the new bond between them. That's the new bond between the star and the dot. So that's how you can keep track of the groups when you're doing these intramolecular ring closing reactions, right? Where we see at carbon 6 has 2 methyl groups. So we have to include those 2 methyl groups in the product like that, right? And this new bond right here between 1 and 6 came from that double bond right there, which is why there's no more double bond here, right? And since this carbon here lost the bond, that carbon is going to have a positive charge. So now, like, this is the broken aromaticity ring, right? That's the end of the second step. Now, the third step, the final step of this mechanism is to restore the aromaticity by doing elimination, right? So I'm going to explicitly draw a hydrogen there. This is when we bring back the leaving group that left. This is the base that's going to do elimination, right? This aluminum here with a negative charge is very unstable because it has 4 bonds, right? And a negative charge. It wants to lose a bond to become neutral again. So this chlorine here wants to leave. So this chlorine here is going to attack the H. An acid-base reaction is going to happen here. This chlorine here is the base. This hydrogen is the acid. And then we're going to make a double bond right there, E1, right? And that reforms our aromatic benzene ring here, right? And that forms these side products, HCl, and our metal catalyst, AlCl3, right? We see that this is a catalyst because it gets reformed in the reaction. We could use this catalyst again in another reaction, but this is a side product, HCl acid, right? Yeah, so when we do the intramolecular reactions, like this right here, I always start my number 1 atom at the nucleophilic atom, the atom that's attacking, the starred atom, right? And then I always go to the atom being attacked, the electrophile. That's my last numbered atom, right? So I numbered this 1 because that's the nucleophile atom. And then I go all the way until I hit the electrophile, right? And the reason why I do that is because this nucleophile here is trying to make a new bond with that electrophile, right? This atom 1 right here is trying to make a new bond with this atom 6 right here, which is this new bond right here between atom 1 and 6, right? And then everything else will maintain the same. Like let's say there was an isopropyl group at carbon 3 in the reactant. You would have to maintain the isopropyl group there. And that's how you can keep track of what groups are on which carbons and not like lose carbons, not add too many carbons in the product. Right. Okay. So any questions on this part A? This should be the final answer here. This is intramolecular Friedel-Crafts alkylation. Intramolecular Friedel-Crafts alkylation. Okay. Are all of these steps reversible? So, the mechanism. Let's see. Reversible, irreversible. This step is reversible. The concerted shift here, I would say, is irreversible. And then everything else from there is going to be irreversible. But this step here should be reversible, right? But if this is a mechanism problem for Lievens test, I think she'll include boxes for you and she'll include the arrows for you, like the reversible, irreversible arrows. But I think that this step here, when we form the good leaving group, is reversible. And then once we do the concerted shift, that's when it becomes irreversible. Right. Why doesn't the AlCl3 go back to the positive charge? Right. So the negatively charged aluminum here, once it loses this chlorine atom, since the chlorine is going away to attack this H to form the HCl, right? This is the HCl part, HCl. They come together to form that. The aluminum now only has 3 bonds, right? 3 bonds to chlorine, and it's like boron. It's neutral and happy with 3 bonds with an empty p orbital, like that. So that it's not like carbon, where if carbon has 3 bonds, it will have a positive charge, a carbocation, right? It's one of those weird atoms that is neutral with 3 bonds. So those weird atoms would be like boron, BH3, aluminum, AlCl3, or iron, FeBr3, right? Boron, aluminum, and iron is going to be neutral with 3 bonds. And all of these here are Lewis acids because they have empty p orbitals where some kind of nucleophile can donate its electrons to the empty p orbital, right? Just like in this first step of the reaction here, this aluminum had an empty p orbital for this chlorine to attack, forming this new bond right here between them. Right? So that's why it's neutral and not positively charged. Yeah. So let's move on to electrocyclic reactions, part B. Okay. So when you see a system like this with dienes and the reagent is light or heat, that's a big signal for electrocyclic reactions, either ring opening or ring closing, right? And here's the table that I like to use. I kind of forgot it, but let me just like try to do it off memory and then see if this is right. Let's see. Let's just do odd. I'll fix it if it's wrong, but this is what I remember in my so far. Odd pair of electrons, even pair of electrons, and heat. Lievens would write heat, or you might see that as a delta symbol, and light, which is H nu. Okay. And then I think it was like this. Con, dis, con, dis. Right. Let me check that actually here. Okay. Okay. So it was the other way around. Right. So the first row is going to be an even pair of electrons. Right. Don't mess this table up, because if you mess the table up, you're going to rotate the groups wrong and you're going to end up with the wrong product. Right. Make sure your table is correct on your note cards, and then you could rotate the groups correctly. And this is supposed to be dis and con. Okay, let's make sure. Even pair, odd pair, heat, light, con, this, con. Okay. So what con rotatory means is that you're going to rotate your groups in the same direction. And the direction that we are referring to is clockwise or counterclockwise, CW or CCW, right? This rotatory is going to mean that we're going to rotate the groups in opposite directions, right? Opposite directions in terms of clockwise or counterclockwise. And here's the thumb rule that you could use to help predict the product if you're ring opening or ring closing, and where to start your thumbs. Like, is it going to start like horizontally, like this? Or is it going to start vertically like this, right? The arrows here are representing the thumbs. Okay, so looking at this reactant here, do you guys think we are ring opening here or ring closing here? Ring closing, right? Because we see no ring so far, and we see this system here is able to close down like this, right? Where those will be the arrows for ring closing. And I'm going to number these arrows, these atoms, 1, 2, 3, 4, which would create this 4-membered ring here, right? Which is this 1, 2, 3, 4. There's a double bond between 2 and 3, right? Because that double bond came from the double bond between 1 and 2, and then the double bond between 3 and 4 made this new bond between carbons 1 and 4, right? The methyl group on carbon 3 stays flat and planar because it was on an sp2 hybrid orbital, and it stays on an sp2 orbital, maintaining the flat sp2 like planar stereochemistry of the methyl group, right? But now we see an ethyl group and a methyl group that was on an sp2 atom, and now it's on an sp3 atom, right? So it could either be like both wedges, or it could be one wedge, one dash, or it could be the other way around, like dash and wedge, like that. To figure this out, this is when we use the thumb rule, right? So how many pairs of electrons are participating in this reaction here? 2 pairs of electrons, right? And the way you think of pairs of electrons is the number of arrows you see. We see 2 arrows, and those arrows will mean the pairs of electrons, which is an even pair. So we're going to look at this row right here. And we have light, which is going to be a dis-rotatory reaction, right? So dis-rotatory reaction, where we're going to rotate the groups in opposite direction. Okay, so now let's look more specifically into the ethyl group and methyl group. Look at the very first atom attached to the system, which is this carbon here. We see that that is going up, right? Up away in the system. Whereas the methyl group is going down, right? We see that they're going away from each other. They're trans to each other, right? So when we're ring closing, we're going to start our thumbs either left or right, right? And then we're going to end our thumbs up or down to represent if it's going to be wedge or dash. If it's going up, it's wedge. If it's going down, it's dash, right? So because I see that one is going up, one is going down, they're going to face away from each other. So I'm going to say my left thumb here, right, is going to go to the left side. My right thumb here is going to go to the right side. And I'm going to say my left thumb is representing the ethyl group, right? And my right thumb is representing the methyl group, where they're going away from each other like that. So if this is dis-rotatory, let's say that I decide to rotate my left thumb, the ethyl group, clockwise, in the clockwise direction. Right? Don't rotate all the way here, because you want to stop at the top or bottom position, right? We just rotate it until we end at the top or bottom position. So I'm rotating clockwise, 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 and I stop here when I'm at the top position right here, right? If I rotated my left thumb clockwise, what direction would I have to rotate my right thumb, the methyl group? If this is a dis-rotatory reaction, counterclockwise, right? So counterclockwise would be going this way, right? Don't go all the way here. Stop at when you go top or bottom. So I'm going counterclockwise, counterclockwise, counterclockwise. They're going both up. So that's how we know that they're cis to each other, right? So that's why the ethyl group here is going to be, let's say, wedge that makes the methyl group also a wedge, cis, right? They're cis to each other. And make sure to put racemic as well, because we could have done it the other way, right? We could have rotated the ethyl group counterclockwise, rotating the methyl group clockwise, right? Where now they're both facing down, both dashes. They're still cis to each other, right? Which is why you get the racemic mixture of this, right? The enantiomer version of that as well. Yeah. Okay. Any questions on this electrocyclic reaction? Okay. So let's move on to part C with the kinetic thermodynamic conjugated diene reactions here. Okay. So we have a conjugated diene here because we have two alkenes that are conjugated to each other, that are adjacent to each other. We have one equivalence of HBr in hot temperature. Does this thumb rule always work? Yes, it would work in all the problems that I've been doing with the worksheet, the chapter 14 worksheet that Lievens posted, and the AETC Mary Jones electrocyclic reaction worksheet as well. Just make sure to practice with this though, because sometimes I have a hard time figuring out what direction is clockwise, what direction is counterclockwise. And make sure to like start your thumbs up or down, where ring opening here is going to be harder than ring closing, because in ring opening, there's a hidden pair of electrons that are resonating, that are reacting in the reaction, and there's also major and minor product, right? So do you guys want to do an example of a ring opening electrocyclic reaction before we move on really quick? Okay, let's do it. Let's do it. Okay, so let's say we have something like this. Okay, and let's react this with, we used light earlier, let's use heat. Okay, so if you have this reactant molecule here, you know that this is going to be a ring opening because you already start off with a ring, and the biggest sign here is if you see stereochemistry. If you see wedges or dashes, then that's another big sign of ring opening, right? So here's the tricky part here. How many pairs of electrons are going to react to open up this ring? And this is a little bit tricky. Yeah, three pairs, right? Where one is going to be here, the other one is going to be here, and then this is a sneaky one here. This would also count as a pair, right? That single bond in the ring counts as a pair of electrons that is doing the reaction, right? Because that's the one that's breaking the ring, that's opening up the ring, right? In ring closing, all the arrows will start from a double bond in ring closing. In ring opening, it's a little bit sneakier because of this single bond right here that counts as a pair of electrons. Yeah, this would be an odd pair. Yeah, so degrees of unsaturation, that's another way to think about it, right? Where a double bond counts as 1 degree of unsaturation, this is another degree of unsaturation, and this whole ring right here is a degree of unsaturation. So that's 3 degrees of unsaturation, or 3 pairs of electrons. So you could replace this table as saying even number of degrees of unsaturation, or an odd number of degrees of unsaturation. And that might be more helpful for Lievens' vocab section, especially because she wants it to be like very specific on like how she taught the concepts. So for the table, it might be best to use her method, right? Even number of degrees of unsaturation and odd number of degrees of unsaturation, but they mean the same thing, right? Yeah, so this would be an odd pair because it's 3. With heat, what would that be? Conrotatory or disrotatory reaction? Are we going to open it up? Yes, disrotatory, because, yep, odd pair heat, disrotatory. Okay. So now we're ring opening now. I'm going to number my template, my base product 1, 2, 3, 4, 5, 6, which is going to be this 6 carbon base products here. What is this? 1, 2, 3, 4, 5, 6. At carbon 3, this ethyl group stays flat and planar because it stays on an sp2 atom, right? But now this wedged tert-butyl and this dashed methyl group is on an sp2 atom. But to figure out if they're going to go down like that, up like this, up like that, we do the thumb rule, right? So when we're ring closing, we're going to slide our thumbs up or down. I'm going to say my left thumb here is my tert-butyl group that's going up, right? Because it's wedged. And I'm going to say that my methyl group here on the right hand is going down because it's dash, right? So if I'm rotating this rotatory, there's 2 ways I could do it. Let's say that I rotate my left thumb counterclockwise, right? Which is gonna face to the left side. And I keep going and I stop at the left side, right? I don't go all the way down like that. I stop until I stop at the sideways, like left or right. If that went to the right, to the left, I'm gonna rotate my right thumb clockwise, which is this way, right? Where now we see that they are facing away from each other. One is going to the left side here, one is going to the right side there. So if I draw that out, I see that the tert-butyl is going to go up, this methyl is going to go down, facing away from each other, right? There is another way that you could draw this though, which is this, right? Let's start the same way, tert-butyl up, methyl down. Now let's rotate the tert-butyl clockwise and rotate the methyl counterclockwise. Wait. Did I do this correctly? Let's see. Counterclockwise, this rotatory, clockwise. Okay, I messed up here, right? Because we said that this was disrotatory, meaning that we have to rotate the groups in opposite direction. If I rotated my tert-butyl counterclockwise, my methyl has to rotate clockwise, not counterclockwise, because this is disrotatory. They have to rotate in opposite directions, right? So if I rotate my methyl group clockwise, they're gonna face in the same direction like that. Yeah, they're gonna face in the same direction. Yeah, right. Con is the same as this as AP. Con is the same. This is up. So con rotatory and disrotatory would not describe what the product looks like, right? Because if you have a con rotatory reaction, your groups could still be trans, right? Con rotatory and disrotatory is describing how you rotate the groups. Con rotatory is when you rotate the groups in the same direction. Disrotatory is when you rotate the groups in opposite directions. Yeah, right. But that doesn't describe like the end product though, because if you have a con-rotatory reaction, the 2 groups can still be trans to each other, right? But the way they rotate is the same direction, right? So the way I rotated this one was wrong. I rotated it con-rotatory at the beginning. So let's try again, right? This is gonna be my tert-butyl up, my methyl down. If I rotate my tert-butyl counterclockwise, this has to rotate clockwise. Now they're facing in the same direction like that, right? So we see that this tert-butyl here is going to go up. This methyl here has to go up as well, like that, right? They're both going on the same direction now. Now let's do it the other way. I'm going to rotate my tert-butyl clockwise, which means that I'm going to rotate my methyl group let's see, clockwise, counterclockwise. Yes. Now they're facing down. They're both facing down, which would give me that product right there. Does that make sense so far on how we got those? Yeah. once I'm done with this problem, I'll go back to the thumb rule chart with the cardinal rotor, this rotor, and where to start and end your thumbs, depending on if you have a ring closing or ring opening reaction. Right. Okay. So now there is a major and minor product though, where this is the major product, this is the minor product, right? Because there's more steric hindrance here since the bulky group is like jamming into the system. That's minor. This is major because there's less steric hindrance here. When you do the chapter 14 practice reactions, she'll draw out both of these. But on the exam, if you do draw out both of them, make sure to label them major and minor just to be safe. So you don't confuse the grader, the TA that's grading it. Right. Okay, let's go back to that chart here. Yeah. Okay, let's move on to the next one. Oh yeah. Okay. So HBr, hot, that's going to be a thermodynamic product. And if we are looking for a thermodynamic product, what are we looking for? The more stable intermediate or the more stable product? More stable product, right? More stable product. Now, this is an asymmetrical conjugated diene, right? Which means that we have to look at the two resonance structures and then choose the best resonance structure from there. Don't choose the more stable product just yet. We got to react the HBr with both alkenes, right? So I'm going to react with the left alkene first. Which carbocation do you think is going to be more stable? The left one or the right one? Which one is going to be more stable? They look equally substituted, but one is actually more stable than the other. The right one, right? Because if you have a carbocation here, that cannot do resonance at all. The right carbocation here can do resonance with the alkene because it is on an allylic carbon. It's at the allylic position, one carbon away from the alkene. So that means that we're gonna filter into the left side, kick out the bromine to get this carbocation here. And because we said that this is on the allylic position, we could do resonance with the double bond like that, giving us our first resonance set here. Okay, where this is a secondary allylic carbocation, this is a primary allylic carbocation. Now let's react with the other alkene in pink. The more stable carbocation is going to be the tertiary allylic. So I'm going to react it like that to get this carbocation right here. And this can do resonance with this double bond, giving us this resonance structure here, where this is a tertiary allylic carbocation. This is a secondary allylic carbocation, right? Yes, I will post this on YouTube and the Discord after the session ends. Yeah, I will, with the timestamp still, so you can skip to the part that you need the most. So now once we have this, which set do you guys want to keep? Which resonance set looks the best for you? The blue one or the pink one? Yeah, the pink one, the bottom one, right? So we're gonna get rid of the top one because it has the more stable carbocation intermediates, right? Now let's analyze what kind of double bond we have. The first one is di-substituted because this alkene here has two groups attached to it like that, right? The right one is going to be tri-substituted because it has three R groups attached to the alkene like that, right? Now, which intermediate, A or B, would lead to your thermodynamic product? Right would be thermo, right? Because we want to look for the more stable alkene product, right? So if you're looking for the kinetic product, you would go for A, right? Because A is looking for the more stable intermediate, the more stable carbocation intermediate. So if you're in cold temperatures, you would go with that intermediate if you're in cold temperature. But since we're in hot temperature, we're going to look for the more stable alkene, which is the more substituted alkene here, right? So now the Br minus that got kicked out earlier is going to come back to attack this carbocation to get us this thermodynamic product here. The thermodynamic product here is going to be this carbocation. So now the Br minus that got kicked out earlier is going to come back to attack this carbocation to get us this thermodynamic product here. 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 To get us this t the more stable alkene product, right? Yeah, hard time drawing out the resonance structures. Yeah, this is when 118A comes back to haunt you. The resonance structures of 118A, like this portion here, resonance is gonna come back. A tip for that is look for a network of sp2 orbitals, sp2, 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 sp2. If those are like in a row, like in a chain, then that's a big sign of resonance, right? Where this is conjugated, or that could do resonance, this is conjugated, this is conjugated, and this is conjugated, right? A network of adjacent p orbitals like this. All these things are considered delocalized or conjugated. A network of at least 3 p orbitals, at least 3 p orbitals that are parallel to each other, right? And the exception of that might be an allene or a accumulated diene like this, right? Because since this carbon here has 3 bonding groups, that carbon there is sp2, this carbon is sp2, but the carbon in the middle is sp hybridized, right? The reason why is because the carbon in the middle has 2 bonding groups, right? 2 bonding groups making that sp. If this is sp2, it has 1 p orbital, which would make a double bond with the middle carbon like that, right? But the middle carbon will have 2 p orbitals, one vertical, one horizontal, like that. So the p orbital of the right side would be horizontal in order to make a double bond with the middle carbon like this. So this is not conjugated, right? This is not a conjugated system because we do have 4 p orbitals, 1, 2, 3, 4, but they're not parallel to each other, right? We need them to be parallel to each other in order for them to be considered delocalized or conjugated, right? Like this, parallel, parallel, parallel. The most parallel thing we have is like the 2 p orbitals here making that double bond. So this is called an allene functional group or accumulated diene, not conjugated diene, right? And this is a conjugated diene right here. Conjugated diene. An isolated diene is when there's no conjugation at all. Something like this, right? Where there is an sp3 roadblock blocking the resonance train, right? Can't do resonance. Okay. So now this is going to go back to the midterm 1 material. The alkene here is going to react with HBr, right? So let's just do that reaction. We know that the tertiary carbon is going to have the more stable carbocation. So the less stable, less substitute carbon is going to get protonated, kick that out, and get this tertiary carbocation here, Markovnikov addition, right? Where the Br minus is going to come back to attack that tertiary carbocation to get our final answer. Yeah. Right. Okay. Any questions on this problem? Okay. Let's move on to Diels order. Okay. So in Diels order, we're gonna look for the diene and the dienophile. So my diene backbone here is gonna be this highlighted portion there, right? This conjugated diene right there. My dienophile is gonna be this double bond right there, right? So the one in blue is my dienophile. The one in yellow is my diene. Everything else is decoration. Everything else are the groups of the diene and dienophile. But they're important though, right? Because you have to like keep in mind of the endo rule. keep in mind of what the out group, in group as well. So now I'm gonna draw a pocket between the diene and dienophile like that, where that's the new bond that's gonna be formed in the reaction, right? So if I draw out the mechanistic arrows, these 3 arrows here, we're gonna get this base cyclohexene product there, base deals auto product there, right? Where this was the diene portion, this was the dienophile portion, and these are the new bonds that was formed between them, the pocket between the diene and dienophile. To keep track of the groups better, let's number them. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, now let's add in the decoration of the Diels auto reaction. So the stereochemistry matters a lot here because of something called the endo rule, which basically means that the out group will be cis to the EWG, and the in group will be trans to the EWG, right? And let's define what an out and in group is. Right. So an out or in group will only be on carbons 1 and 4, the way I numbered it here, right? Only those atoms. If you see any groups on any other atoms, don't call those out or in groups, right? If there's a group here, don't say that's an out or in group. Don't say this is an out or in group, not an out or in group, not an out or in group, right? The out or in groups will only be on carbons 1 and 4, the ends of the diene like this right here, right? Look at the pocket right here between the diene and dienophile. If the group is going outside of the pocket, that's called an out group, right? We see this ethyl group here, that's going outside of the pocket. So this ethyl group right here is considered my out group. Where inside of the pocket, we see that CH2 chain inside the pocket, which is going to be considered our in group, right? Are you guys familiar with determining what groups are your EWGs and EDGs? Like how to tell what's an EDG, what's an EWG? Yeah, I'll show you an example of a Diels order problem where the groups are in groups instead of out groups after this. Okay. So, okay. I made a video on how to determine whether a group is an EDG or EWG last night, which I posted on the YouTube. But to summarize everything quickly, so now we can move on to the other parts of the exam in this review session. An EDG is going to be something that is partial negative charge or fully negative charge. An EWG is going to be something that is partial positive charge or fully positive charge. Some weird things are going to be R groups. R groups like methyl ethyl isopropyl are EDGs. Halogens are EWGs, like chlorine, bromine, iodine, right? And then you have to look at the very first atom attached to the system. Very first atom, right? So if we look at this dienophile here, what functional group do you think of when you see CHO? CHO. Aldehyde, right? Which is going to look like this. And it is an EWG because if you look at the very first atom attached to the system here is dienophile. It is partial positive charge because it's attached to an electronegative oxygen, making that an EWG. Okay. Would this nitrile CN here be an EDG or EWG? This whole group here. Would this be an EDG or EWG? EWG, right? Because the very first atom attached to the dienophile is partial positive charge, making that an EWG. It wants to withdraw electrons. It wants to take electrons, right? Since it's missing electrons right now. Okay, so now we have two EWGs here. Two EWGs. Which means that we're going to get two different sets of enantiomers, right? So what I mean by that is for the first set of enantiomers, let's consider the aldehyde as the EWG, right? And if our aldehyde is the EWG and I choose to make my ethyl group a dash ethyl, what stereochemistry would the aldehyde have to be in relation to the ethyl group? If I am choosing my aldehyde to be the EWG, it has to be cis to it, right? So if I made the ethyl group a dash, that aldehyde would also have to be a dash like this, right? And so now we'll look at the relationship between the nitrile and aldehyde. Are they cis or trans to each other in this alkene that they are on? Are they cis or trans to each other? Cis to each other, right? So we have to maintain that cis configuration. So if that aldehyde was dash, this nitrile would also have to be a dash, just like that, right? Now, we see this ethyl group is on the other end of the alkene, which is trans to the nitrile. So I'm gonna make that ethyl group a wedge like this because it's trans to the other groups. So the ethyl group on carbon 6 is gonna be wedge. Okay. Now on carbon 1 and 4, there's a CH2 connecting them, and they are in groups, right? And based on the endo rule, the in groups are trans to the EWG. So I'm gonna draw the CH2 like this. That's one CH2. This is another CH2, and that's a bond connecting them, right? This is CH2. To make that more clear, I'm gonna highlight that in red, that bridge right there, connecting 1 and 4, which is this bridge right here, connecting 1 and 4, like that. Right. So this right here, and its racemic, its enantiomer would be one set of products. You might say in this form, which is easier to see that bridge like this, right? Where let's number it the same: 1, 2, 3, 4, 5, 6, and let's highlight the portions. This yellow portion is the diene portion. This blue portion is the dienophile portion. This red bridge is that red CH2 connecting 1 and 4. It's like a basket, like thing, like a handle, right? You could see that bridge more clearly here, right? And then the pink is the new bond between diene and dienophile. And then let's put in the decorations: ethyl at carbon 4 going down, aldehyde going down, nitrile going down, ethyl going up, like that. Right, so that's one of the products, and it's racemic form or enantiomer form right there. Right. But is this part here confusing? Like drawing this form right here? Is this like where it got confusing? Yeah, so the ethyl and aldehyde are gonna be both dash because of the endo row here, right? It looks like they want to be trans to each other to avoid steric hindrance, right? But let me explain to you the endo row more clearly. If we have this diene right here and dienophile right here with this EDG and this EWG, and we react that with heat, this is the product that we are going to get, right? And if we use the endo rule, we want those groups to be cis to each other. This looks like the less stable product, and it is because the endo product from the endo rule is the kinetic product, right? It's the one that forms the fastest. And I'll show you why here, right? Because you would expect these groups to avoid each other, so they would be trans to each other, right? Like one wedge, one dash. But that's not the case, because if we look at the intermediate here, where I draw the diene like this, hovering over the dienophile, like this, and then I draw the p orbitals of the diene and the p orbitals of the dienophile, we want those p orbitals to overlap with each other. To think of it like the kinetic product in the conjugated diene reactions, like halogenation. The kinetic product comes from the more stable intermediate, right? This one here will get the most stable intermediate because it increases the secondary p orbital overlap. So that's just a lot of words, but what that basically means is more resonance, more conjugation, basically. Right? Where we see that the p orbitals here are overlapping better, which would increase the stability of the intermediate, right? Which is why that leads to the kinetic product or the endo product. That's why the endo product is the kinetic product. Great. So this is going to be more for vocab, where if she mentions exo product, the exo product is going to be the thermodynamic product, the more stable overall end product, thermodynamic. Right. So if we use the same reactants as I did right here, the thermodynamic product or the exo product would be if the outgroup is trans to the EWG. So this is the exo product, right? Because this is the overall more stable product, avoiding steric hindrance, right? But it comes from a less stable intermediate, because if I draw the intermediate like this, we are going to see that the p orbitals are not going to align anymore, right? They're way too far from each other. So there's no overlap, right? No overlap. Less stable intermediate, more stable end product. So an analogy that I like to use is that the thermodynamic product is your most stable end product, but it comes from the less stable intermediate, right? It's like studying for an exam. If you study for an exam, you're stressed, you're unhappy in the studying time, right? Like you come from an unstable intermediate, but at the end you end up with a better grade, better stability. You are more stable, you are more happy, right? But that requires more energy, more time to get to that point, to get to the thermodynamic point, which takes longer. That's why you need energy and time to get to the thermodynamic product, right? To get to the more stable product, but it comes from the less stable intermediate, right? You are not stable in the process. But in the kinetic product, like let's say you party, you go out to drink, you hang out with friends, go party, go crazy. In the moment, the intermediate is very happy, very stable, right? The most stable intermediate, but the end product is less stable. The end product is less stable. That's the kinetic product. Right. Yeah, hopefully that analogy makes sense. Yeah. For EXO, it's just out group is trans to EWG instead of cis. Yes. For EXO, the out group is trans to the EWG instead of cis because that is the more stable end product, less steric hindrance. But it comes from the less stable intermediate, right? The intermediate here is less stable. No secondary overlap. Or less secondary p orbital overlap. Or less resonance, less conjugation in the intermediate. Right. Just endo rule, but the other way around. Yeah. Where the exo product would require a lot more energy, a lot more time. So if you give it enough heat and time, then it would eventually go to the exo product. But the first product that gets formed is the endo product. Endo product. But in predictive product reactions, right, always draw the endo product. Don't draw the exo product. Right. In Diel's order, we always draw the endo product as the answer. That's more of a vocab thing. It's more of a vocab thing. Last, but I was wondering, will they be enantiomers or constitutional isomers? Right. So this right here would have an enantiomer version, right? I didn't draw the other set yet. The other set would be constitutional isomers with this set right here. Right. I'm about to draw the other set, which that set would be constitutional isomers with this set here. is it because both were EWG like Cho and CN that it is racemic? So it's racemic because all of the chiral centers here could have been flipped, right? Because if I chose to make this ethyl group to become a wedge, this would have been a wedge, this would have been a wedge, and then the wedges would have been dashes, right? Everything gets flipped. Every chiral center gets flipped. That's enantiomers. Like every single chiral center, like every wedge gets flipped to a dash, every dash gets flipped to a wedge. Those are enantiomers. That's why we say racemic, right? The EWG here and the out and in group is just talking about the endo rule, which is the most confusing part about Diels order, this endo rule. Here. Right. So let me draw out the other set and then we'll work on more Diels order practice to get this down. Right. Where we see that there's another thing as well, like with chemistry. If this is an EDG, imagine like it donates electrons directly into the system. It would push electrons all the way up on the other side, giving that carbon a partial negative charge. This dienophile here will have a partial positive charge on both ends, right? I could draw that more clearly if that didn't make sense, but because there's partial positive charges on both ends, we could flip this dienophile upside down. And if we flip it upside down, this is what we would get. Where the CHO would be here, the nitrile would be here, and the ethyl would be there, right? So your other set would be this here. Let me just draw that here. There's a lot going on. So everything stays the same, but this time the aldehyde is at the bottom, the ethyl is at the bottom, and the nitrile is at the top, the ethyl is at, like everything here stays the same. So if you just leave your answer as this in the answer, I think you should still get full credit. If this way is like more difficult to interpret and think about, like the bicyclic ring, then don't worry about that, right? But the difference between these here is that the nitrile and aldehyde and ethyl flipped spots, right? They just flipped around because I flipped the dienophile upside down, where these would be constitution isomers of each other. These are constitutional isomers. Yeah, let me explain when the flip happens again for Diels order. That's going to talk about chemistry. Let's see. If one EWG was more stronger than the other, you will only draw one product. So that's gonna be not for Diels order, right? In Diels order, don't worry about the strengths, relative strengths of EWGs. If you have two EWGs like this, then just flip them upside down to get your other products. You would have to worry about the strengths of EWGs and EDGs in EAS reactions, electrophilic aromatic substitution reactions. Okay. Draw both of the constitutional isomers and racemic for both of them as well, right? So these are your four products you get. Two enantiomers here and another set of two enantiomers there. So these are the four products that were included. No, you can always flip the dienophile. Now let me go over why we have to flip that more clearly. So in Diels order, the basics of it is going to be this diene reacting with this dienophile, right? And I'm going to draw out the resonance structures of this to make the arrows more clear, to show the movement of what's going on here. So I'm just going to draw these resonance structures to explain this concept. Okay, does this resonance structure make sense of the diene and dienophile so far? Like how I moved these arrows and got these charges here? Great. So now once we have the resonance structures, and we draw the pocket between the diene and dienophile like this, we want the charges to be aligned to each other. Opposite charges attract opposite charges. So they do align to each other because the negative charge here is on the same side as that positive charge. The negative charge here is on the same side as that positive charge, right? So this negative charge here will attack that positive charge. This negative charge here will attack that positive charge to give you this Diels order products here, right? Where we could say that's 1, 2, 3, 4, 5, 6, which is this 1, 2, 3, 4, 5, 6, right? We see that there's a new bond here, a new bond here from those attacks, those arrows right there. So that's what's happening behind the scenes, behind the Diels order reaction, right? Where the charges are aligned to each other, opposite charges are on the same side, and they react with each other. Now, this could get more complicated when we put EDGs and EWGs on them. So I'll show you what I mean by that here. So let's look at this diene right here with this EDG, OCH3. We see that this oxygen here has a pair of electrons that can directly donate electrons into the system like this, pushing this double bond over there, which pushes this double bond onto that carbon right there to get this resonance set here. Okay, does that make sense so far? Like how I got that resonance structure? Yeah, I want to make sure I go over this step by step, so then you guys get the concept of why we flip things sometimes and we don't flip things other times, right? Now, if we have a dienophile like this with an aldehyde EWG, this would withdraw electrons from the dienophile like this, giving us this resonance structure. Right. Now, if I highlight my diene in yellow and highlight my dienophile in blue, these are the backbone of the diene and dienophile. And if I draw the pocket between the diene and dienophile like this, that gets formed. Ignore the other charges. The other charges will not matter in this case, right? Look at the charges of the diene and the charges of the dienophile and see if they align or not. In this case, they do align. So we could go through with the reaction without flipping anything, right? So if we go through with the reaction, we're going to get this product here where we didn't have to flip anything, right? Okay, here's a challenge problem for you guys. What would be the stereochemical relationship between these groups here? Would they be cis to each other, or would they be trans to each other? It might help if I draw the pocket between them like this. Cis to each other, right? Because this is outside of the pocket, we call that the out group. This is the EWG, and based on the end of rule, the out group is cis to the EWG. So if I make that a dash, this would also have to be a dash. It could have been wedges as well, like both wedges instead of both dashes, which is why we put racemic. Okay, so now let's increase the difficulty of this now. Let's say that we have this EDG, and we have this EWG. And I'm going to draw out the NO2 in its Lewis structure to show why it's a strong EWG. Right? And now I'm going to draw in its resonance structures again to show the electronic configuration behind this reaction. Boom. When you do this reactions, you don't have to draw out the resonance structures, right? This just helps you think of when to flip or not. Boom, boom. Okay. Let's keep track of where our diene is and where our dienophile is. Our diene is right here. Our dienophile is right here. Positive charge. Okay. Let's draw the pocket between them. Notice how the charges are not aligned anymore because the positive charge of the dienophile here is not on the same side as the negative charge on the diene right there. They're not on the same side. They're not aligned, right? So you cannot go through with the reaction as it is and get this product, right? That would be the incorrect product because the charges are not aligned based on what we see on the resonance structure, right? So what we got to do is we got to flip one of them. We got to flip either the diene or dienophile. I like flipping the dienophile because it's smaller and it's easier to draw out, right? So let's redraw the diene like that. And the dienophile they gave us was this. I'm going to flip it upside down to get this right here, right? And now I'm not going to draw any resonance structures for you guys anymore because I did that at the beginning just to show you guys what's going on behind the scenes, right? And I don't want you guys to do that on the exam because that's going to waste so much time on the exam. And then these tests are like very like time constrained. So what I want you guys to do instead is think about what's going on behind the scenes like this. This EDG here is going to donate electrons into the system like that, pushing this double bond down, pushing this double bond over here, giving this carbon a negative charge. So I'm going to give that carbon there partial negative charge. I know there's a negative charge on that carbon because of the resonance that's going on here, right? Which is what I drew out earlier for you guys here, right? But don't draw out all this stuff on the exam, right? Just think about it like this. It goes all the way down, putting a negative charge there. That's all you need to do, right? And now for the EWG, it's withdrawing electrons. So it's taking electrons from the dienophile, giving this carbon here a positive charge because it's losing a bond, right? And now we see that the charges do align between the diene and dienophile, right? That's much faster than drawing out all the resonance structures, okay? And now we could proceed with the Diels order product like this. NH2, let's make that dash, NO2 dash racemic. Okay, right. So now this is the correct product, not the one here, right? Because the charges did not align. Okay, let me give you guys something a little bit more. Wait. If you guys see something like this, right, like an R group attached to the diene, this R group, is this an EDG or EWG? It's an EDG, right? And it's an EDG by induction because there's no pairs of electrons to donate into the ring or into the system, right? So it can't do resonance, but it is an EDG by induction. And if it's an EDG by induction, just imagine there's a pair of electrons here that would go down, push that down, where we would have a negative charge here, right? So R groups are going to be considered EDGs. Okay. Another thing that you might encounter is this right here. So let's say we have OCH3 here. And I'm going to number this 1, 2, 3, 4. Where would our negative charge be? 1, 2, 3, or 4 if the EDG was here? Where would the negative charge be? Think about the resonance structure here. Right, so 4, that's what we're used to seeing, right? Because we're used to seeing the EDGs on the end, and it always puts a negative charge on the other end, the opposite end, right? But in this case, the EDG is not on the end. It's somewhere, it's in the middle of the diene. So when I draw in the resonance structure, like I go down there, where would this double bond go? Would it go? Yeah, it would be 1, right? Because let me actually draw out the resonance structure for you for this one because this is new. If the EDG is in the middle, if we draw the resonance structure, we go down, that pushes this double bond onto atom 1, the nearest atom now, instead of the furthest atom. Right, so I think you guys get the point, but let me just draw this quickly. OCH3 plus negative charge. Right, so when you see an EDG in the middle, the negative charge is at the nearest atom. If you see an EDG at one of the ends, the negative charge is at the other end, based on the resonance that's going on like that. Right. Okay. So I'm gonna give you guys a diene, and I want you guys to tell me where the negative charge is gonna be at. Okay, let's say this is 1, 2, 3, 4. Where would the negative charge be at in this diene? Yep, 1. Because this EDG here is donating electrons, giving that carbon 1 a negative charge. This is also an EDG, which if we imagine it to have negative charges, it will go down and give that carbon negative charge as well. Right. So the negative charge here will be on 1 for that diene. Now let's go back to the practice exam, Diels order, where we see that this R group, like we said earlier, is an EDG. Yeah, 1 applies for both R groups, right? Because the R group at the other end right here is still at the end product, right? And so if you imagine negative charges there and we do resonance, it's gonna push that there, push this there here, giving a negative charge on carbon 1, like that, right? So if we go back to this problem, now I think it should make more sense why I put the negative charge on carbon 1 here, right? Because this R group right here is donating electrons, which pushes the negative charges on the other end of the diene. For the dienophile, we have 2 EWGs here. So if we withdraw electrons from one EWG, we get a positive charge at this end. If we withdraw the diene with the other EWG, we get the positive charge at the other end. So we get positive charges at both ends of the dienophile, right? So the Diels order reaction would happen as it is drawn here because the charges do align in the pocket, right? The negative charge here is attracted to that positive charge, so that can go through with the reaction. But if we flipped it around, it could still go through because if we flipped it around, there will still be positive charges on the dienophile to align with the diene, like this. Where is it? If I flipped it around. Yeah, if I flipped it around, it's gonna look like this. Let me draw this. Right, where this is the pocket between the dienophile, partial negative charge on this end because we have an EDG here, and then partial positive charge on both carbons of the dienophile, right? So we see that they are still aligned because there's positive charges on both ends. Would you say if there are 2 EWGs on the dienophile, we would flip it for sure to get the constitutional isomers, right? So if you have EWGs on the dienophile, like 2 of them, then you would always have to flip it to get all the correct products, right? So make sure to flip the dienophile if you have 2 EWGs on the dienophile, right? Okay, let me give you guys a similar problem to this that's going to test on a similar concept, and I worked on that for like 2 to 3 minutes, and I'll go over this. Okay, with heat. Try this problem for actually 3 to 5 minutes. 3 to 5 minutes. Okay, so for this one right here, the first thing I like to do is locate where my diene backbone is and locate where my dienophile backbone is, which are these highlighted portions here. The one in yellow is the diene, the one in blue is the dienophile. And then I like to draw the pocket between the diene and dienophile like that, right? And now I like to figure out where my charges are at. So let's look at the diene. Let's say this is 1, 2, 3, 4, and dienophile 5, 6. Where would the negative charge be? Would there be one negative charge or would there be multiple negative charges? Yep, there would be multiple negative charges at what carbons? 1 and 4. That's right. Because when we donate electrons into the diene with both EDGs, we get negative charge there, and we get a negative charge here. So there will be a negative charge on 1, negative charge on 4. Now, let's look at the dienophile. Where would the positive charge be at on the dienophile here? 6, yes. Because this is the EWG right here, the NO2, which would withdraw electrons from the dienophile. And then if this carbon is losing a bond, that's going to have a positive charge, right? So our positive charge here is going to be on carbon 6, right? At this point right here, as it's drawn, do we have to flip it? Do we have to flip anything? Or can it go through as it is right now? Yep, it could go through as it is right now, where let's just say that this is the base cyclohexene deals other product like this. Where this was 1, 2, 3, 4, 5, 6. The ethyl at carbon 2 stays flat and planar on the sp2 atom. Okay, so now let's think about the endo row here. Let's see here. If I make my EWG, the NO2 here, a dash, like let's say this is a dash, NO2, what would be the stereochemistry of the OCH3 and the NH2? Would it be a wedge? Would it be a dash? It would be a dash, right? Because these are out groups since they are outside of the pocket, right? They're outside of the pocket means that they have to be cis to the EWG. So it's, oh shoot. Yeah, so you're right. It's gonna be as it is, and we also have to flip it to include all of the products. Let me share my screen again. Screen stuff. Okay. There we go. Okay. Yep. And H2. So now, what would the methyl group be on carbon 6? Would it be a wedge or a dash on the product? A wedge, right? Because it's not going to be a dash because we have to look at the configuration between the NO2 and methyl group, right? So on this alkene right here, this NO2 group is trans to the methyl group, right? And if it's trans to the methyl group, we have to maintain that trans configuration. So if the NO2 is dash, we got to make it wedge, right? Like that. I don't know why it's not updating on Zoom. There you go. There you go. Okay. Why isn't there a wedge dash on carbon 2? Yeah, so there's not going to be a wedge or dash on carbon 2 because this carbon 2 here, do you know the hybridization on carbon 2? Is it going to be sp, sp2, or sp3 hybridized? sp2 hybridized, right? Because it has 3 bonding groups, 1, 2, 3. And if it's sp2 hybridized, it's going to be flat and planar because that's the shape, trigonal planar, flat and planar. Like everything on an sp2 atom is flat and planar. There's no wedge, no dash on sp2 atoms. Right. Okay. So that's one of the products and its racemic form because everything could have been flipped. I mean, yeah, flipped. But that's not the only set of answers that we could get, right? Because we could have flipped our dienophile upside down to get that, right? Which would lead us to this product here. I'm just going to redraw this to make it straight. Boom. OCH3. Same kind of concepts for the endoral stereochemistry, but the regiochemistry is different now. This is just flipped. And it's able to flip because when we look at the pocket between the diene and dienophile, the charges are still aligned, right? Allowing us for the reaction to go through again, giving us this other set of enantiomers here, right? Where these enantiomers are constitutional isomers to those enantiomers. Okay. Any questions on that? On this Diels order? Okay. Now let's go on to this one here. Okay. So when you see this benzene ring with the R group, and you see this group right here, you have to draw this group out in bond line structure, which would look like this. The tert-butyl CH2 COCl, right? Where the CH33 is on this central atom, and then the CH2 is this CH2 here, and then the CO is that carbonyl, and the Cl is that chlorine right there. For the EDGs, would have one that is stronger than the other where the partial negative charge is affected? Yeah, so in this cases right here, if both EDGs can donate electrons by resonance, right, then both partial negative charges would do the Diels order reaction, right? So don't worry about the strengths of EDGs, EWs in Diels order. Worry about that for EAS reactions. But it would matter if you have like say something like this. Let's say you have a methyl group here and an OCH3 group here. This is when it matters. This is when you choose the stronger EDG to put the negative charge, right? So if this is the case, where would the negative charge be stronger at? What atom? What atom would the negative charge be stronger at? 1, right? This is going to be a big negative charge at 1 and a small negative charge at 4, right? Because this is an R group which donates electrons inductively, right? So this is when you would choose one over the other, right? But if the EDGs are both donating electrons by resonance, then that's when you flip it and draw out all of the products. Okay. So now this is going to be Friedel-Crafts alkylation because we have an acyl group. Yeah, there's no carbon-carbon wedge bond here because this is an sp2 atom. That's an sp2 atom. Oh wait, I think my wife. Oh shoot, yeah, my Wi-Fi got cut off Am I laggy? Am I still cutting off? Okay, okay. That's good. Let me know. We said earlier that R groups are EDGs. Do you know if EDGs are orthopara directing or meta directing? Like, will they direct the electric file? To the, wait, hold on. Technical difficulties. Okay. Yep, orthopara directing. So hindered product. Let's see. Okay, my phone is still charging. But am I okay now? Am I still cutting off? Am I still laggy? Okay, it's better. It's good. So, shoot, it might be better if I turn off my video. Okay, so I'll turn it off for now, and I'll um if we want to look for the major product, aesthetically hindered one, where would this acyl group be attached to? The ortho position or the para position? Para position, right? So a trick to predict the product here is to only attach this acyl group here, right? Where this chlorine here is the leaving group that will leave. And that's gonna substitute the benzene ring right there, right? So this acyl group was attached to the chlorine. but now it's going to be attached to the benzene ring. Tert butyl stays the same. Acyl group will be right here. Okay. Now, when you see zinc mercury HCl, that's going to be Clemmensen reduction. That's only for the reverse reaction to turn it back into the carbonyl. So it would be NR. Right. So for this one right here, this one, okay, actually, before we go over that, let me give you guys the helper reactions. Right. Let's say we have a benzene ring like this, and we have an NO2 group, and let's say we have a carbonyl group like this, right? And then we reduce it with one of these three reagents. You're going to see any of these three reagents here: zinc, mercury, HCl, or iron, HCl, or hydrogen and palladium, H2PD. All of these three reagents here are reducing agents that would reduce the NO2 into NH2 and the carbonyl into alkane. So it just gets rid of that carbonyl. It goes bye-bye. It goes away, right? But it reduces this NO2 to NH2, right? So now, let's say that you want to get back to the NO2 or the carbonyl. This is going to be more selective, right? Where if you want to get your NO2 back, you're going to use CF3CO3H or NCPBA. Most likely this, because I've seen more of that in Lievens class, that's going to convert the NH2 back into the NO2. But that would not affect the alkyl group. That would not go back into the carbonyl. If you want your carbonyl back, you got to use drones, CrO3, H2SO4, and water. That would not affect the NH2. The NH2 would stay the same, right? But that would bring back your carbonyl here, like that. Okay, so this is reduction. These are selective oxidation, right? Because this one here would reduce like both the NO2 and carbonyl down, but depending on what you want for oxidation, you can use either or reagent, right? So based on that, let's go back here. What would this zinc mercury HCl and heat do to this reactant here? Right, you can look back at the chart. Yep, it would get rid of the carbonyl. Bye-bye oxygen. Bye-bye carbonyl. Right, goes bye-bye. Get that guy out of there. Like that. Okay. Yes. So on the key, she said that you may include the minor product, which is the ortho position, right? Which is why I recommend you guys drawing out both the major and minor product and label them. So then your TA doesn't get confused, right? This is the minor product here, the one that I'm drawing out for you guys, right? Where there's more steric hindrance going on there. Minor. Yeah. You guys can take a screenshot of these reactions where these are reduction and these are selective oxidation. Okay, there is another helper reaction that I want you guys to know, which is desulfonation. So let's say we have a benzene ring that has some kind of random group, ethyl, bromine, and SO3H. What reagents would completely get rid of this SO3H? Would go and get rid of that SO3H? Yeah, I think this is like one of the newer lecture material, like the chapter 16 ones. H2SO4 H2O and heat. Nice, nice. Yep. H2SO4, H2O, and heat. And this is a major synthesis player reaction, right? This is a major reaction to use in synthesis because this will block off the para position. Yep. NaOH works with water and heat as well. So acid or base with water and heat. Acid or base with water and heat would get rid of the SO3H. Okay. And then tomorrow night, we'll probably go over like synthesis problems and the vocab section. But today, I want to get down the reactions and mechanism. Okay, let's move on to the next one. Let's do this one. So when you see NBS or NCS, we're gonna add a halogen, but what atom specifically is the halogen gonna be added onto? Like what position? Can we use H3O plus? Yeah, instead of H2SO4, you could also use H3O plus as well. H3O plus, water and heat. That would work as well. What needs to be added to benzene so nothing can added? Oh, I think you're talking about the Friedel-Crafts limitation reaction, right? Like this is important right here. Friedel-Crafts reactions do not work on deactivated rings. So if you have something like this, NO2, NO3, H2O plus, this is no reaction. But if you have this, and you do the same reagents, then you're going to get these. Right, where this is major, this is minor, right? Because this is considered a deactivated ring, and this is considered an activated ring, like that. Yeah. Yeah. What if you have both an activator and deactivator? So if you have an activator and deactivator, if your activator is way stronger than the deactivator, like bromine, then it would go through. If you have, like, let's say NH2 and even a strong deactivator like SO3H, then it could also go through, right? But the group that would direct the Friedel-Crafts reaction is the activator. The EDG would direct where the Friedel-Crafts reaction would go to, ortho or para to that. So if you have an activator or deactivator, it can go through, but it would go through where the EDG directs the acyl group to go ortho or para to it. Oh, right. So what Benedict just said, right? This is a very important thing. If you reduce, okay, yeah, this is gonna go on to the other chapters of chapter 16, which will complete chapter 16. If you reduce NO2 to NH2 using H2PD, and you try to do Friedel-Crafts reaction, like this right here, an important thing to note is that this NH2 here is a stronger nucleophile than the benzene. So the benzene will not react with this acyl group. What you would get instead is this right here. Right. Let me go connect to my hotspot really quick so then it's less laggy. Less laggy. Okay, I'm back. I'm back. It should be much better now. Right. Yeah. So now this concept that what I'm going over right now is talking about NH2 and OH are stronger nucleophiles than the benzene. So they will react with the Friedel-Crafts reagents instead. Right. So if you have like, let's say a phenol benzene with an alcohol attached to it, and you try to do if Friedel-Crafts acylation, do a Friedel-Crafts acylation reaction, the benzene will not react with the Friedel-Crafts reagent. The alcohol will, creating this here. Right. Okay. So now let's say that you do want to create an acylated benzene ring with an OH or NH2 to it. So this is going to go onto protecting and deprotecting the OH or NH2 group, right? Because for synthesis, let's say that you want to convert this benzene ring with the alcohol into this acylated group with the alcohol still there, right? You cannot go here directly by using this Friedel-Crafts reagent, right? In synthesis, what I recommend you to do is that just copy and paste whatever this is, right? Which is why I drew it out in that same orientation and put a CL right there, which makes it quicker to predict what reactant you need for Friedel-Crafts acylation. AlCO3 H2O plus. That's not what you're gonna get. What you're gonna get instead is where the alcohol gets acylated. So the oxygen here gets acylated instead, right? So what we could do is do Williamson ether synthesis to convert the alcohol into an ether here. The OH will become OCH3, right? What do you guys think is going to happen between the OH and the NaH here? What's going to happen between them? The H is a very strong base. Strong base. So if it's a strong base, it's gonna look for the most acidic acid, most acidic hydrogen, which is gonna be this alcohol hydrogen right here. So it's gonna deproteinate that alcohol to make this phenoxide here, right? That oxygen will have a negative charge. It gets deprotonated. And then we do SN2. We bring in the CH3I, attacks that, kick that out to get that ether right there. Now, this is a weaker nucleophile where we could now do the Friedel-Crafts reaction we want to add that group to the para position. Wait, did Lievens go over this? If you didn't, I don't want to like overwhelm you guys with all this material here. Like, did Lievens go over protecting the OH or H2 group and deprotecting it? Or was it like she was like too much material, let's skip over this? So now we have the acyl group on where we want it to be on the benzene ring. To convert the OCH3 back into the OH, we use concentrated HI, right? Which is a 118A thing. Don't worry about the mechanism. Just know that this concentrated HI will convert this OCH3 back into the OH. It will deprotect the OCH3 and convert it back to the original OH we have. Yeah. Okay, so that's protecting OH. Now let's go to protecting NH2. Yeah, this is probably one of the newer materials, newer lecture material. So sorry, like you might not be like too familiar with these. But the reason why we want to do this is to add an acyl group when there is an NH2 or OH in a way. Right, so think of it like this. When you see an OH or NH2 on the benzene ring, right, that's a super activator. It's a super strong EDG. Like it's so strong that it will take over as a nucleophile for acylation, right? So if you see an OH or NH2, the acylation part would go onto the NH2 or OH, right? Because it's a super strong EDG. So the point of these reactions here is to make it weaker, and then we could add the acyl group to the benzene ring without the NH2 getting in the way. And after that, we could deprotect it to convert it back to the original thing, right? So to protect the NH2, we're gonna add an acyl group to it like that. You might see it as an anhydride as well, but it's gonna mean the same thing as an acyl group, right? Where the thing that we're attaching is this acyl group here, and the chlorine or the acetate is just the good leaving group, right? Once we do that, that NH2 right here is going to be acylated to get that amide right there, which makes this a weaker nucleophile. Then we can do the Friedel-Crafts reaction we want to add that acyl group onto the benzene ring, like this. Boom, boom, boom. And H. Okay. And now to deprotect it, we gotta use acid, water, and heat as the first step. Actually, it's more common to use the base because this is gonna go into 118C, right? This is the beginning reaction of 118C. So it's gonna be base, water, and heat, or you could use acid, water, and heat, and a second step, base, right? Just know the deprotecting reagents that would deprotect this amide back into the amine right here, right? Don't need to worry about the mechanism because that's gonna be 118C, but the synthesis is a 118B thing. Yeah. Okay. That's the end of chapter 16 reactions, like towards the end of it. So let's go on to NBS. When you see NBS, draw out the radical on the allylic position. So this is the allylic position, so I draw out that radical right there. We know that this radical can do resonance with alkene, like this, where I draw single hook arrows to show the movement of one electron, right? When I draw out that resonance structure, I'm gonna get this here, right? Where the double bond is now here, the radical is now here. And now where the radical is, just imagine a bromine is attached there to get your two products. So that product comes from that intermediate. This intermediate will get us this product here, right? Where bromine was just attached onto that carbon right there, right? Don't like forget about that carbon. That carbon is still there, right? Some people, they draw the product out like this, which is wrong, right? It's missing a carbon, right? Because that carbon is still there. If you draw like this, you're getting rid of that carbon, right? So make sure that carbon is still there. You're just making a new bond from the radical to that bromine. New bond from the radical to the bromine, like that. So those are your two different products there for NBS, right? Okay. That was predicted product. There's these ones as well. Okay, so do you guys want to do HNMR for the remaining of this session, and then tomorrow's office hours we could like do the mechanism, synthesis problems? Yes, let's do it. Okay. Spectroscopy. The first thing we do is to calculate the degrees of unsaturation, which is 2C plus 2 minus H minus, what was it? Minus X plus N all over 2, right? We have 15 carbons, that's a lot. 21 hydrogens, 1 chlorine, and 2 oxygens. Okay, this is going to be a big molecule. Plus 2 minus 21 hydrogens minus 1 halogen. We have 1 chlorine. We have 0 nitrogens, right? All over 2. The office hours tomorrow is going to be 9 to 10 p.m. 9 to 10 p.m. I can't do longer because I have to study for my my test on Thursday, same day as you guys. Okay. But I'm hoping that this session and tomorrow's session could help you guys review for the midterm. 2 times 15 is 30. 30 plus 2 is 32. 32 minus 21 is, oh shoot, math. 14. Wait. 32. That's 9 plus 2. That's 11. 11 minus 1. Okay, 10. 5? Did you guys get 5? Oh my gosh. This is going to be so embarrassing if I get this wrong. Okay, 30, 32, 21, 11. Okay, yeah, it should be 5. Yeah. 5 DOU. So we have at least 4 DOU, which means that I think we have a benzene ring somewhere in the structure, right? Because a benzene will have 4 DOU, 3 double bonds and 1 ring. 3 plus 1 is 4. 4 DOU. And the DOU is going to be, the benzene hydrogens are going to be between 6 to 8, right? But let me show you this pattern here, which will most likely show up on the HNMR on the exam with a di-substituted benzene ring, right? Ortho, meta, or para, right? So let me actually separate this like this. So then you guys have a clear chart of this, the differences between ortho, meta, and para in HNMR. Okay, so ortho, meta, para, right? And let's say the R groups are different. One is R, the other one is R prime. R prime. Okay. The benzene hydrogens are going to be between 6 to 8. Right? The hydrogens directly on the benzene ring. Between 6 to 8. 6 to 8. These are the H's. Let's look at ortho. for these ortho hydrogens here, they're all unique, right? One is going to be A, like let's say that's A, this is B, this is C, this is D. There's no plane of symmetry here. We see that hydrogen A has one neighbor, so hydrogen A should become a doublet. Hydrogen B has two neighbors, so it should be triplet. Hydrogen C has two neighbors, so that should also be triplet. Hydrogen D has one neighbor, so that should be doublet. Right, and the integration for all of these is one. There's one hydrogen of each, right? One A, one B, one C, one D. So what you see this pattern between 6 to 8, two doublets and two triplets, you know your benzene ring is going to be ortho. Right, there's going to be two substituents that are ortho to each other. For meta, on the other hand, let's say this is A, B, C, D. A has one neighbor, doublet. B has zero neighbors, singlet. C has two neighbors, triplet. Oh, triplet. D has one neighbor, doublet. Right, so this is A, B, C, D. Integration of one still. The biggest identifier of a meta benzene ring is this singlet right here. So when you see a singlet between 6 to 8 and like everything else, then you most likely have a meta benzene ring where the two substituents are meta to each other. Right? Para is the easiest to recognize because now we do have a plane of symmetry, which is down this middle right here, where this is going to be A, B, B. Right? These hydrogens have the same chemical environment. These hydrogens have the same chemical environment. Hydrogen A has two neighbors, doublet. Hydrogen B has two neighbors, doublet. But now the integration is going to be 2, right? So to know that your benzene is di-substituted, right, you will have to have 4 benzene hydrogens between 6 to 8. They have to add up to 4, right? 1, 2, 3, 4, 1, 2, 3, 4, and then 2 plus 2 is 4. That's how you know if your benzene is di-substituted. Then to tell whether the groups are ortho, para, meta, or para to each other, you then look at the patterns here, right? If you see just 2 doublets, that's para. If you see singlet there, that's meta. And then ortho is like the wonky one, the 2 doublets and 2 triplets. Okay. Any questions on the patterns here on the ortho, meta, para? Okay. Now let's see what we have on the HMR in the exam. So we see between 6 to 8, there is a singlet. There's 4 benzene hydrogens, so we know it's di-substituted. There's 2 doublets and 1 triplet. So I'm going to say that we have a meta benzene ring. Right? We have substituents on the benzene ring that are meta to each other. But I don't know what those 2 groups are just yet. Right? But I know that they're going to be meta to each other like that because of this pattern between 6 to 8. Right? Which is using this chart right here. Okay. So we see that there is a peak between 9 to 10, which is the aldehyde peak. So this right here is going to be my aldehyde hydrogen. How many neighbors will this aldehyde hydrogen have, right? If it has 3 subpeaks? 2 neighbors, right? So my other fragment is going to be like this, where it's 2 neighbors or these 2 neighbors right here, right? And that accounts for my last DOU, the carbonyl, right? Because I already used up 4 DOU from the benzene, 1, 2, 3, 4. I have one more. That one more is going to become the aldehyde right there. But to make sure that I have the aldehyde right there, I know that the aldehyde is going to have a carbonyl sharp peak at around 1700 and a sharp peak at around 2700 in the IR, right? So let's confirm that we have those peaks in the IR. We do have the 1700 peak here, which is the carbonyl peak, and we do have a peak around 2700, which is the aldehyde peak, right? So that matches up. So I know for sure that we are going to have an aldehyde in the molecule. I'm going to also say that this 1600 is the alkene peak, which is the alkenes of the benzene here, the C-double-bond-Cs, right? The 1600 sharp peaks. And then I'm going to ignore everything else, fingerprint. This is the regular sp3 carbon hydrogen, so we could basically ignore that as well. And then this one could be the sp2 carbon hydrogen, which is the benzene hydrogens. And we do have a broad peak at 3300, which represents what functional group, especially when we see this broad peak as well with an oxygen. OH, alcohol, right? So we do know that we have an alcohol as well somewhere in the molecule. So let me draw out my fragments down here to make it more clear. So my aldehyde with 2 hydrogens, my meta-benzene ring, and my alcohol. That's what I have so far, my puzzle pieces so far. And that fulfills the DOUs, the alcohol broad peak, and the aldehyde thing. Okay. My iPad's like dying right now. It's like not working. Okay, there we go. Okay. So we already accounted for that, accounted for this, accounted for that. When you see 6 H's here, that is a doublet, and 1 H here with a lot of neighbors, what common group do you think of back in monosine A? Like what common fragment do you think of? What common group? Is it going to be tert-butyl, isopropyl? Isopropyl, yes, isopropyl. Because the 6 hydrogens with 1 neighbor here are going to be these 6 hydrogens here, right? Which I'm going to highlight in yellow. Like these 6 hydrogens here are those 6 hydrogens right there that have the same chemical environment. And its 1 neighbor is that 1 blue hydrogen right there. And if it has 1 neighbor, it's going to be a doublet, right? And I'm going to say that that 1 blue hydrogen is this one right here because it has a lot of neighbors. It has at least 6. 1, 2, 3, 4, 5, 6 neighbors. But let's see how many it has actually. So 1, 2, 3, 4, 5, 6, 7. 7 subpeaks, meaning that it will have 6 neighbors, right? 1, 2, 3, 4, 5, 6, 7 subpeaks, 6 neighbors. That means that, do we want this carbon to have any hydrogens at all or no? Do we want to add more neighbors to this hydrogen? The blue hydrogen? No, right? We don't want to add any more hydrogens to that carbon, right? So now there's multiple ways we could think about that. We could put so what can we do? Let's see. Okay, I'm just put that purple group here right now and see later on. Right? But I know that there's no hydrogens here, right? Because we don't want any more neighbors there. Okay, let's move on to the alpha region right here. 2 to 3 is the alpha region. 2 hydrogens, 2 hydrogens. Okay, I'm just gonna start combining pieces together and see what I get. Okay, so I'm just gonna guess here. I'm gonna put my isopropyl group on that benzene ring to get this structure right here. So I'm just gonna draw out random stuff now and pray. I get it right. Okay, so I'm gonna put isopropyl group here, where I see that this carbon here still has 6 neighbors. 1, 2, 3, 4, 5, 6. There's no hydrogen here, so that still works out, right? And then let's see, but it's not at the alpha region, but I'll say let's do that. CH2, 2 hydrogens, 1 neighbor, aldehyde, and alcohol. CH2, CH2. Okay, yeah, the ones in the middle here are always the hardest. Like the ones in the crazy ones here, the 2H2H with a lot of neighbors. Let's figure out how many neighbors this would have. 1, 2, 3, 4, 5. 4 neighbors. 1, 2, 3. 2 neighbors. 2 neighbors. 1 neighbor. Okay. 4 neighbors. How can this 2 hydrogens have 4 neighbors? It could be in the middle somewhere, right? The 2 hydrogens with 4 neighbors could be, let's say, these 2 hydrogens right here, right? Which I'm gonna highlight in purple for you guys to show that those 2 hydrogens in purple are these 2 hydrogens here that have 4 neighbors. these two hydrogens right here, I'm gonna highlight in pink for you guys to show you guys that those two pink hydrogens will have two neighbors, and it's on the alpha carbon as well, which is gonna be these two hydrogens right here, right, which is between 2 to 3, and it has two neighbors. Let's see, what can we do? What else can we do? Two hydrogens with two neighbors here. And then I'm gonna say that these two hydrogens here that are alpha, they're gonna be alpha to the aldehyde with one neighbor, right? So I'm gonna say that these two hydrogens right here are gonna be highlighted in blue, which are gonna be these blue hydrogens here with two neighbors. So how do you use blue? Let's use red. Wait. Something's not adding up here. Alcohol. Okay, the alcohol is very deshielded. Like it's very high up here for some reason. It probably would have to be on the benzene because we already have an N piece with an aldehyde. Yes. Oh, what would have to be on the benzene? Like what group would have probably be on the benzene? What group do you think would be on the benzene? See. Second isopropyl the alcohol. The alcohol. Right. So I'm leaning towards the alcohol now because we see that this alcohol here is very deshielded. It's like around 6 area, right? But when we see a regular alcohol on a regular alkane, it usually shows up between 3 to 4, right? The broad peak. But this broad peak is very high up here at 6, which means that it's gonna be more deshielded next to a benzene ring like that. So let's stick with that. And the isopropyl group could be somewhere else. Could be let's say, okay, let's keep track of how many carbons we used up. We used up 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now we gotta add our isopropyl group and aldehyde somehow. Let's see. 2H, 2H. Let me put an aldehyde here, and let me put the isopropyl group here, right? Because if I make this my red hydrogens right here, which are these red hydrogens right here, I only want those two hydrogens to have two neighbors because it has a triplet. It has 3 subpeaks. And to maintain the two neighbors that it already has right here, I don't want this carbon to have a hydrogen, right? But right now it has one hydrogen, so there's something going on here. Which might be the alpha hydrogen. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm missing one carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. What is that one? The CL. Oh my god! Oh, wait. Yeah, I forgot. There's a CL here. Oh my god, sneaky CL. Right. So don't forget about this CL right here. Right. Okay. Yeah. So look at the chemical formula as well. Look at your chemical formula to keep track of all your atoms. So that Cl right there is gonna be right here. Now that would work out because these two hydrogens right here will only have two neighbors, which are these two purple hydrogens right there. Like this is where I was getting stuck. I was like, we don't want any hydrogens right here, right? Because we don't want any more neighbors for these two hydrogens. But let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Hello? We have 15 carbons. Wait, am I missing something? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Two hydrogens. Isopropyl. Carbonyl. Oh, yeah, we use it two oxygens already. The oxygen from the alcohol, oxygen from the aldehyde. 15 carbons. that, you step this, you step that. CH2. Which are these CH2s with one neighbor? Okay. One neighbor. One neighbor. Okay, okay. Okay, I see what's going on here. So the CL is gonna be right there. I'm gonna put this here. And then I'm gonna put wait, actually CH2 right here. No, the CL is not gonna be there yet. The aldehyde is gonna be right here. The CL is gonna be right here. Let's see what's going on. Okay, let me wait like this right there. Okay, so now wait, no, that's not one hydrogen, that's two hydrogens. It has one neighbor. Okay, okay, now put the CL back to here. Okay, so let's highlight this in orange. The two H's here that are alpha to the carbonyl are going to be these two H's here at the alpha region. We see that those two H's has one neighbor, which is the aldehyde hydrogen neighbor, which is why it's a doublet. Right, so that's the only one neighbor it has, the aldehyde hydrogen. The red hydrogens here only has two neighbors, which are these red hydrogens here with two neighbors, right? This carbon here has no hydrogen, so there's no neighbors for this hydrogen or that hydrogen right there, right? And then this would fulfill all the carbons now, hopefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 carbons. Okay, that's good. Let's see if we have 21 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 hydrogens. So that's all of the hydrogens. One chlorine right here, and two oxygens. Okay, so this would be my final answer. Let's see what the key says. The key says let's put it in red. Benzene, alcohol, meta to that, CH2, that chlorine up here, isopropyl here, CH2, aldehyde right here. Right, so which is the same thing as what we got. This is the same thing, it's just rotated, right? So we got it, but that took like, I don't know, like 10, 15 minutes. Oh, I don't know when we started, but that took a while. Wait, keep track of the atoms, like the chlorine here. It is a lot of trial and error as well. So if you do mess up, like try to go backwards, try to like do new things, but like getting the final product here, like that's getting like most of the points, like full points, right? But if you get your fragments, like the meta, benzene ring, the isopropyl, the alcohol, the phenol, the aldehyde, right? That's gonna give you a majority of the points already, right? The finishing touches is just getting this specific structure here, right? So I would spend most of the time getting the fragments first, finish up everything else, the reactions, predicted product, synthesis, mechanism, vocab part down, and if you have time at the end, which is like rare, try getting the final specific pieces together, right? Okay. Would we get an NMR that's trisubbenzene on the benzene in the midterm? So if it's a trisubbenzene, then you would have only 3 benzene hydrogens, right? And that's how you know if you have a trisubbenzene versus a disubbenzene versus a tetrasubenzene. If you have a tetrasubbenzene, then you only have 2 benzene hydrogens, right? So it could show up on the midterm. But I think that it's going to be a disubbenzene where your R groups are either going to be ortho, meta, or para to each other. Like this is the more common one. Right. Did you guys follow through with what like what my thought process was on this? Yeah, no problem. On the HNMR. Oh my gosh. Yeah, so thank you for mentioning this CL here. I forgot that we had a chlorine on this HNMR. That was very important right there. because if that's there, right, then that would mess everything up. Like if that was a hydrogen instead, then that would mess up the neighbors of this and this, making it not make sense. That's good. Yeah, I don't use the CNMY at all to predict the structure, but you can if it helps you. But I don't use it. I don't use the CNR to predict my structure. I don't even like know what it is. But in 150C it could help, but I don't know. I don't use it. Yeah. No problem. Uh, no problem. Uh-huh. Yeah. Good luck. Good luck. I will maybe see you guys tomorrow night. It's office hours. And yeah. I'll send the recording. Office hours is 9 to 10 p.m. tomorrow. 9 to 10 p.m. Mhm. Good night. Good night. Yeah, office hours are online. It's gonna be the same Zoom link. Yeah, thank you. Thank you. I need the good luck on my test. So I actually like don't know what's going on right now. I need to study. Mhm. Yeah, thank you. Hey Ryan.
Hello?
Hey, how are you?
Long day?
Yeah, long day, long day. Let me go drink water really quick. I need
Yeah.
a little water break. Ooh.
Is everything that you just like said like reviewed like for the past 2 hours just like on like what you're studying, or is it different?
It was a midterm review session for the midterm they have on Thursday, midterm 2.
Oh, not your test.
Yeah, not my test. I'm not taking this test anymore. Like I'm just tutoring.
Ooh.
Yeah. I need to start studying for my own test like soon.
Hmm. Soon. Wait, what time are you gonna go to sleep?
I'm gonna sleep. Actually sleep early, wake up early, huh? I probably sleep by like now, wake up like early, go to the library early.
How
Uh,
early?
how early? So probably be there by 6, or I
Hmm.
don't know. Wait, let's see. What can I do? Because tomorrow after school, I do plan on studying with a group of people. But before that, I want to get it down like myself first, because I study like better alone if I don't know anything. And then once I have an idea of what's going on, I like studying in the group to ask questions, bounce ideas with each other. So I might just stay up kind of late tonight until I get everything down and then sleep in, so then I can study with the group tomorrow. So that's probably what I'm gonna do tonight.
Oh, so it's all last minute and like you have to got like that test on like what, 8 o'clock? 8
Oh,
8
the test is on
a.m.?
Thursday, not tomorrow. Test is on Thursday.
Oh yeah, that's
Yeah.
good.
Not tomorrow. If it was tomorrow, then I'm cooked.
Hmm. That's good luck,
Yeah.
honestly.
Yeah, thanks. How was your school today? Like, how was your day today?
How was my day? So
Yeah.
basically, I guess I slept like at 1, but like the normal would be like 2, which is
Mhm.
better. And probably I'm gonna go to sleep at 12 today.
At 12 today? I see. That's
Yeah.
good.
And I don't know, it's just me feeling really, really tired. But like I didn't take a nap. I didn't like eat breakfast or lunch. I just went back home on my bike. And like the bike ride is like 3 miles,
Was
which took
it
me
3 hours? 3 hour bike ride?
no 3 miles.
Oh, 3 miles. Okay, that's good. That's good.
Takes me like around 25 minutes
Mhm.
total. Hmm. And
Yeah.
basically I didn't like, and I just like ate like a whole mountain of food, and then I like got home and I just I like was ready to like study at 5:30.
Mm-hmm.
But I still haven't like I still gotta like write an essay and I still have like mind maps to do.
Oh, mind maps. Like your own mind maps to study for the test, right?
Mine no, they're like mind maps that like you just like fill out. They're like a worksheet for like, oh, you just read this website as a web quest. You just read the website and then you just like put all the information down. But it's
Uh-huh.
not due. It's like a notebook check where they just check it at the like for the end of the semester. But like I kind of need to like do the readings because like the readings like on like microbiology are super important for understanding what the heck are they talking about.
Right, right. The readings, like, so you get
You
context
review it
background.
all at home, and then you come to class knowing what they're talking about.
Yeah. Dang.
Mm.
That's crazy. Wait,
They
when is
didn't
your
even.
first exam?
Uh, that was like last week. Yeah. The class average was 71%.
71%. Yeah, I remember you told me
Yeah,
that.
all like periods. Yeah, you told me. I told you that. I remember.
Right.
Mm. Honest, they told me that wasn't bad because like I scored 71%, which is the exact average.
The exact average. Oh, how are people like talking about it in school today? Like were they going crazy?
They're going crazy. I feel like everybody is just like keeping it to themselves, but like I could still feel the tension, just like in that class. It's just like nobody really asks that many questions, and nobody like she has first lunch, and most of my friends have first lunch, and the teacher has first lunch, and like nobody actually like interacts with the teacher. It's mostly they have their own group, and they all just bounce around questions in their own group.
In on own group thing. That's good. Like, do you like feel like you could study better in the group setting, or do you study better alone?
I think I studied better in a group setting right after last year I did like a Zoom call with like one of my friends and like it was for AP World and like we just
Mhm.
like we're gonna finish all the AP World homework we were assigned over winter break and like
Ah,
we just blasted through it in one day, one sitting,
wow.
like 3 hours, all of
Dang.
the readings. It's like yay.
That's good. That's good. Like if you're able to do that with a group as well, like without getting distracted and like just stay focused, and that's good.
Mm. Like just like FaceTime calls, just like
Dang. Like the blasted through and everything.
yeah. And now it's just like for me, I like when I told you about that YouTube thing, it really does work. Like all I did was like watch one actual like video today and then like everything else was just like music distracts me also. So like I don't really use it when I'm writing, typing or like reading.
Yeah. Oh, like you do everything in silence. No
No,
music, no like.
everything every I don't actually have anything in silence. I just like literally just changed the algorithm to just only be music, study
Oh,
music.
sad music, right? Like lo-fi or piano, classical music. Like what kind of music do you like ambient, forest, fire sound, cozy sounds?
Uh I guess yeah, mostly ambience and
Ambience. I see.
floats like slow tempos and stuff like that.
Mm-hmm.
Honestly, I'm like the only one asking my teacher for like like questions because like nobody's really answering stuff, and she only goes over the stuff that we think that will be like um confusing, and then everything else is just up to us. And that's what happens with the 71% average. Is like holy.
It's 31% average. I know. Like when you get to college, like that's gonna be like pretty normal. Like some like of the averages here are like 50%, like 40% on some professors. Like it's pretty low, pretty
How many
low.
people are in your class?
So the big classes, like the lower div classes, there's like hundreds, like 200, 300, 400. But once you get to the upper div classes, it gets smaller.
Hmm.
Yeah. Well, that's what when I was at UC Davis. But right now at my grad school, there's like it's like a high school class. It's like 30, 20 people each class.
That's good.
Yeah,
Like,
yeah.
the funny thing is that, like, in periods 1, 2, 3, and 1, 2, 3, I literally have, like, all the same people.
No, all the
Everybody
same people.
the same 20 to 20 people in my class.
So you get to know them. Like it's like a cohort. Like you get to be close to them, closer to them.
Yeah, I just have to like I have a study group, not a study group, but like it's just like all in microbiology, and just like we're just sending photos to each other, or like send me that, send me that. It's like okay.
Yeah, that's good. Like sharing resources. Do you guys have a Discord server with each other or
We aren't that
group chat?
close. We just
Oh,
we just send pictures of like the material.
pictures as a
Yeah.
like a group chat text message, or is it
Yeah,
like
like
one to
Instagram group chat,
oh
basically.
Instagram group chat? I see, I see. Yeah, you guys should start a Discord server or something, you know?
Mm-hmm.
Dang.
Did you like wait, did you already like brush your teeth and take a shower yet?
No, no, I'm gonna do after this.
Oh.
Yeah. Yeah, how about you? Did you do it yet?
Yeah, I did it like while you were
Oh, while I
tutoring.
was giving the review session.
Yeah.
Dang, yeah. Today was the longer one because I made it a 2 hour review session just for the midterm. But
Mm,
tomorrow I can't do that because I have to like study for my exam, but I'll still have it 9 to 10 p.m.
mm.
And then the one on Thursday night, I don't think anyone's gonna show up because it's right after the midterm. So we could just talk.
Yeah,
So we
that's
could
what I was
talk.
planning. Cause like I'm just saying that like if I have like 7 hours a day after school, I get off at like 3:37, and
Uh-huh.
like I have like I get and then I get like home, I rest a little bit, and then I like start my work at like 5 o'clock ish. And so I have like around 7 to 8 hours, and I would go to sleep around like 12 to like 1 o'clock. And then that way I'll get all like everything done. Also, tomorrow's a minimum day. So I'll get out at like 2:37 instead of like 3:37. So I'll have like 8 hours, 8 or 9 hours instead.
I see. Yeah, that's good. Like today, I got pretty lucky because I left school early. Like that's not like usually the case. And when I got home early, I just like took a nap. And my friends wanted to go meet up at like Seven Leaves at the library to schedule a trip to Las Vegas this winter break. And then we got some food and then went home and then did the review session
Hmm.
here. Okay. Dang.
Wait, does
And
your friend also in the same field as you, or different?
My friend, the one that you saw like few episodes ago, Joseph, he's
Joseph.
dental, like pre-dental like you. He wants to
Yeah,
get
I
to
know. I
yeah.
can't forget Joseph.
Yeah. I know. Dang.
Hmm.
have you like do you go party often or no? Like you
Party.
yeah.
I went to one birthday party over the summer, but that was literally it.
mm,
Mm.
birthday
I
party.
mean, I usually just work out at my house. I'm at my and then I tried catching up on like AP Chem, but then I realized that it wasn't in my schedule, and I have it next semester.
Next semester, yeah. And when
But
you
I'm
take
glad.
AP Chem, send me all your notes, your lecture notes, and everything, so then I could learn it with you, like relearn it with you, and then we
Mm.
could work through it together. Like send me the homework columns, the assignments, the textbook readings, all your lecture notes that you take, so then I could like like
Some
study with you.
teachers just like when I went into the A push history room,
Uh
they
huh.
literally just had all the freaking um college board class code plus the Google Classroom for each period. Like they did not care. They just signed it up.
Dang.
But like, hmm, I probably need to ask someone if they have the code, or like ask someone to say to their teachers that they forgot the code and just tell them to write it on a post-it note.
Dang. Post
Maybe. Yeah.
like the notes or what for the
The
code?
actual classroom, like Google
The actual
Classroom, that
classroom,
has
like to
all
get
the
in, like, to get
materials.
enrolled in.
Yeah.
Oh, dang,
Mhm.
crazy. Like so people can still like get into class at this time of the school year.
You can still get into like an archive classroom. Yeah, probably.
Archive classroom. Like, what the heck is an archive classroom?
It's like a Google Classroom, but like it's not like
Oh,
being used at
like
all.
previous semesters classes.
Yeah.
Ah, all right.
Mm.
I see. I see.
They had to probably create a new one every single year because they don't want to reuse the same one. But
The same year, right? Like they reuse the tests and everything. Like having those
yeah,
books are actually really
if I use
useful.
the
Like
new one, it would just be like I have to wait for them to finish it, and it would be awkward because the teacher would be like assigning the test, and like I would be like there, like not even in the class, and I still like have access to the test, which is like bad. They,
no.
yeah. So like I guess I would like learn the content, but I wouldn't like have like access to like the quizzes and tests because that would be like cheating because they would
Mhm.
probably assign like the same ones every single year.
Right. I know. I know. Like my school right now, like I don't know. If you have access to like the old like material like from upper quarter or like somewhere, then like you have like an advantage, you know, because like you know like what's gonna be tested and everything.
Hmm. That's true.
Right, right. So it's all about connections and resources.
It is really about that. They did like we did like Google Forms. It's just like, what would you give your advice or like explain how you did well on the test, and then basically just like, fill out all the homework, read the notes, just create a group. Don't like study alone, or like at least like have someone to explain the stuff to. Blurting, wait, what's it called? I, literally, I just like wrote on my hand on my notes, but then I like washed my hand.
Oh yeah,
Just like
for the exam, like you wrote note stuff on your hand
no,
and
I
then
didn't. No, I was just like just scribbling down stuff on my hand, and I was like, oh, I forget. Uh, I don't know.
dang.
It's just blurting. No, it's just saying everything that you know, and then like there's one other one that would start with. I forgot. Hmm.
Yeah, that's crazy. You gotta like learn all these techniques, all these stuff to do to just like you know do well in these classes.
Yeah.
Right.
I mean, this is like the micro is like the first class I've ever like thought like had the lowest
Average.
average. Yeah,
Yeah. What average are you used to? Like 90, 80,
around 80s, around
around
80s, but
80s? That's yeah.
never went below that because
Dang.
like all my classes are like with biotech kids.
Right, right. Dang, that's crazy.
They're all good at their classes.
It's like a wake up call to them. Like they gotta change up their study ways for
It
that
is
class.
basically like a wake up call.
Yeah.
I let me just read you something. Let's
Uh-huh.
see if you have time. It's just like an essay, but it
Oh yeah. Send me the essay or read it to me like on Thursday office hours. Right, because I think I'm gonna
sure,
start
I just have it right now. I could
brushing
just
my
send it
teeth
to
and
you.
showering to study for my test. But like save the essay so that we could like see it on Thursday office hours or
I just send it to you right now.
yeah, or just send it to me. Right, right. And we could talk about it on Thursday. Yeah.
Mm.
Uh-huh. Right. Okay. So I'll go. Let you go. Sleep early, and I'll go. Set up some studying stuff, and I'll speak to you again tomorrow night and
Uh,
on Thursday.
yeah, but like the thing
Uh-huh.
is that I want to like have a free day on Thursday, just like to talk and also do my work at the same time. So
Yeah.
I probably just like sacrifice like a couple of hours just so I can get everything done and settled, so I don't have to like.
Right. And then we could just work on stuff together, like on Thursday. You know, like we don't have to just talk. We could just like work
Yeah.
and do homework study. Like it can even be longer than an hour. Than if we are studying, then like not
Hmm.
just talking. Like if we're studying, then we could like just like have it longer. You know, longer than an
Yeah.
hour if we're studying. Yeah.
Mm.
Huh? Sounds good. Like we could do like study together, like Pomodoro technique. Like uh, do you do 25-minute and a 5-minute break, or do you do 15-minute and a 10-minute break?
Oh, so I don't get tired that much,
Yeah.
like
So you just
since
keep
I'm
going.
like I just keep going, but like
Uh-huh.
I just change the song on my YouTube playlist, and then I just keep going. That's it.
I see. I see. I see. Okay. Okay. Well, we'll figure out a system that works for both of us, and then we'll do that. But when no one else is in office hours.
I the system that works for me is just like I'm just depending on the person not to like get tired or like just stop, so I just keep going.
Sure. Sure. It's like a
It's
motivation accountability thing, huh?
a competition kind of
Competition.
thing.
It's good. It's good. It's good competition, pushing each other.
Yeah, it's just like I'm staring at them doing their work, and it's like,
Yeah.
okay, I'm not gonna stop yet.
Yeah. Like we could do that. Like maybe like we could arrange a time in the weekend, or it's like sometime like me and you are both free, so then we could just like study and do that, for our
Yeah,
exams. Yeah. Well, we'll talk more about that on Discord or school. I'll see you guys. Talking to you, Ryan.
yeah. See ya.
Yeah.
We can talk
See
more
ya.
about it. Yeah.
Yeah. Bye.
Good luck. Sleep tight.
Yep.
Yeah, with 6 o'clock, so you got like six
Yeah.
hours.
Yeah. I know.
The average sleep is for the US is 6.5, so you're kind of already past that because you'd be getting 6 hours of sleep, but it's okay
I know.
because
I feel bad though. Like I want like at least 7 to 8, 7 to 9 hours, of sleep.
I mean everybody in my know is already tired, but it's okay. Don't forget to do like what 21, 22 push-ups.
22 push-ups, right. Gotta do
Yeah.
22 push-ups. Yeah.
All right. See ya.
Yep. See you, Ryan.